going back to our last lecture about angular momentum, we're just going to do a quick little recap for this next problem, which also uses the key relationship of angular momentum. So, like I stated, angular momentum is comprised of moment of inertia, I times w, which is the angular velocity, and is the equivalent of linear momentum's m times v. And we know that I is some form of mr squared, some constant front. And then the w is just the tangential speed v over the radius of whatever's spinning. And then the key relationship is just to conserve angular momentum, meaning that this product is the same before and after. So I1 times W1 equals I2 times W2, which is the main idea you need in this next problem 4. Question number 4. It says a spherical star is spinning at initial angular velocity W, and then it collapses to half its original radius without losing any mass. And then it asks what the basically angular velocity will be after the collapse. All right, so the key here is conservation of momentum. We have moment of inertia 1 times angular velocity 1 equals moment of inertia 2 times angular velocity 2. That's conservation of momentum. Momentum 1 equals momentum 2, and for spinning, angular momentum equals moment of inertia times angular velocity. Pretty simple so far. So at the beginning, we know that the moment of inertia for just a spherical star is mr squared. Mr squared is the moment of inertia at the beginning. We can say that r is the radius of the star before it collapses, and then it starts spinning at an angular velocity w. So that's the initial momentum, mr squared w. And then the final momentum is going to be m, but instead of r, we have r over 2 because the star has collapsed to half its original radius. So equals mr over 2 squared, and then we don't know what that final velocity is. Okay, so right away we can cancel out m's. It's the same on either side. And here we have r squared over 4, and here we just have r squared. So we can cancel out an r squared, and this becomes over 4. So we just have basically w equals 1/4 times what? Clearly, this final angular velocity is going to be 4 times w. In order to make up for the lost moment of inertia, it's going to start spinning faster, so we get the answer of E.